Sorry about that. So, okay, so from 3 to 4, the first derivative is positive, a negative meaning the function is decreasing, and second derivative is positive means the function is a concave up, right? From 3 to 4. So what does that look like? What does that look like? From 3 to 4. And 4 to infinity, the last interval here, function is increasing because the derivative is positive, and also concave up because second derivative is negative. So if you follow this closely, if you follow this closely, do you see any inflection point here? Meaning the points where the function changes its concavity. Or let's start with critical points. Do you see any inflection points here?
There are no inflection points.
I think there are.
Key points at 1 and 3.
1 and yeah.
I think you're right. 1, yes. At 1, on the left side of 1, the function is on the left side of 1, meaning in the interval from 0 to 1, the function is concave up, second derivative positive. On the right side of 1, second derivative negative, meaning the function is concave down. You're right. And you said it 2, right? No, you said 3.
3, yeah.
Yes. On the left side of 3, that is on the interval from 2 to 3, second derivative negative, concave down. You're right. Can you assemble this information and draw your own graph? Meaning, I put x-axis here, y-axis here, and can you imagine a graph with this information? We all can have different answers. Just assemble this information and draw, sketch the graph. So this is 0, 1, 2, 3. On the left side of 0, the function is decreasing. On the right side of 0, the function is increasing, meaning we have a critical point there at 0. Okay, at 0. So, and on the left side of 0, function is concave up. At 1, there's inflection point. It will concave up, right? Concave up. Then at 2, the increasing decreasing behavior changes. So at 2, then at 3 also the concavity changes. It's still concave down. On the right side of 3, the function is concave up. Where is 4 gone? Hold on. So let's say there is 4 here. How about that? Have you captured all the information? So at 1, there is inflection point here. And at 3, on the left side of 3, concave down, right side of 3, concave up. So this is one important concept you should understand and you should be able to use being a student of calculus 1. Okay? This is, so this captures a lot of things. This captures uh, very important concepts. Okay, and and do this type of problems. You know, when I was a student like you, I used to enjoy this type of problems than just finding the derivative or integral of some function. Okay, just take the information and try to come up with a graph and see uh, what the signs of first derivative on some interval means and second derivative and so on. Okay, so just do some problems like this, then you start, you know, enjoying this type of problems, and this helps you to understand the concepts of the function, the behavior of the function on some intervals. Okay, so I really encourage you to do this type of problems. So the same thing here. So this is what we just did. This is very similar to the actual answer here. Okay, in the next slide. Okay, so well, if we have time later, we'll come back to this. I don't know if you find some time to look at these steps. So okay, so what we want to do here is, please let me know if you don't hear me because I'm holding my iPad in my hand and sometimes I just grab the speaker. So we want to graph a function with that information, with the information of where the function is increasing, decreasing, critical points, inflection points, and other information without using TI-84 or any graphing software. Okay, so what do you need? So what do we need? So first, number one, we want to see the domain of the interval. Number two, if there are any symmetries. I don't know if you remember, symmetries means if the even function is it's symmetric with respect to the y-axis. Odd functions are symmetric with respect to the horizon. That means it's even function, y equal to x squared, and so on. And then that helps us to determine the graph. Okay. Then number three, see the first derivative, second derivative, and determine whether the function is increasing or decreasing. Number four, critical points, inflection points. So many information here. Okay. Identify the extreme values. Look at any asymptotes. Okay. Particular asymptotes, horizontal asymptotes, oblique asymptotes. Find any intercepts. Do you want to do this? Let's do one problem. Okay. And again, this is the summary of a lot of things we have already done in this course. You have already done in this course. Okay, so if you, well, it would be good, it helps us you to understand if you either have this in front of you, if you have a textbook or anything, let's just put this in front of you. So with that information, let's try to follow all those steps and graph this function. You might be wondering why this professor is teaching all those things, because we can just put this function in our graphing calculator or in software and just graph the function, right? We can do that, but we also have to understand and do graph the function using that information. Okay, so are you all ready?
Yes.
Okay, so number one, what is the domain of this function? What do you call this function? What do you call this function? Is it rational function, root function, polynomial function, trigonometric function? What do you call this function? This is a polynomial function, isn't it? What do you call this function? This is a polynomial function. Okay. What's the domain of a polynomial function? All real numbers, negative infinity to positive infinity. Okay. So is this an even function or odd function? How do we know? Replace x by negative x and see if what you get. If replace x by negative x, so you have negative x cubed divided by 3 minus 400 negative x. What is negative x cubed? Isn't it? You factor out negative, what is left there? That means it is negative of fx. That is the definition of odd function. So this is odd function. That means what? It is symmetric about the origin.
I have a
Okay,
question.
please.
How'd you get the negative 4 the negative f of x?
No, we are checking whether a function is odd or even. Okay, so if you replace, when you replace x by negative x, and you get the same function back to itself, this is even function. When you replace x by negative x and you get negative of that function, odd function. For example, fx equal to x squared. Replace x by negative x. What do you get? Back to itself, right? This is an example of even function. On the other hand, so this function, the function we are talking about here, let me take a simple function here. Fx equal to x cubed. Replace x by negative x. What do you get? As negative x times negative x times negative x, 3 times. That is negative of this original function. That is an odd function. Okay, so even in the graph, odd function means it is symmetric about the origin. Odd function means it is symmetric about the, what did I say? Even function means it is symmetric about the y-axis. Odd function means it is symmetric about the, when you graph the function, it is symmetric about the origin. If a function is not odd, then does it have to be even? No. Okay, but if that happens, if one of that, so if this happens, even function. If this happens, odd function. Understand that?
Yes. Thank you.
Clear? Okay, good. Let me erase this. So our function here, the other way to see this is all the powers of the variables are odd. So this, our function here, the function we're talking about, is an odd function. Okay, what's the next? Find the derivatives and determine the critical points, and find the inflection points if there are any. Okay, so let's do that. Number 3, third step is derivatives. Okay, so f prime x is 3x squared divided by, we still have 3 minus, what's the derivative of 400x? 400, right? 3 cancel out. So we have So we have x squared minus 400. What about the second derivative? Just the 2x. Correct? Are you following me?
Yep.
Good. Now we have domain, we have symmetries is odd function, so it is symmetric about the origin. Now we have the derivatives. Fourth step is find the critical and inflection points. Okay, I'll define critical points first. You set the derivative equal to 0, right? Derivative equal to 0. So what is our derivative? X squared minus 400 equal to 0. So solve this for x. Okay, solve this for x. What do you get here? Take square root of 400.
Positive and negative 20.
Yes, you know what? I was just putting positive, right? And I was hoping the answer like you just gave. Yes, which is positive negative 20. So we have two critical points here. Okay, we have two critical points. A critical, let's say, when I say points in the plane, it has to be an order pair xy. So sometimes we just say, we just abuse the language and say x equal to 20 and x equal to negative 20 are the critical points. By that we mean, well, when we say critical points, this has to be in order pair. Okay, so okay, critical points. Okay, then inflection points. Possible inflection point. That may not be inflection point, but possible inflection point. So what do? You set the second derivative equal to 0. The second derivative, 2x. So x equal to 0. Do you just call, well, plug in. So 0, what is the y coordinate of 0? If you plug in that 0 for x in the original function. So we have x in both places, so it is 0. So I have a question for you. It 0, 0, can we just declare that 0, 0 is an inflection point? The answer is no. Okay, so we set that second derivative equal to 0, and we find that 0, 0 is that point, but that doesn't mean that 0, 0 is the inflection point. What is the inflection point? The point where the function changes its in concavity. We call them, so here we set the first derivative equal to 0, then we find that x equal to 20, positive negative 20. We call them critical points. Okay, we call them critical points. We don't have to change, we don't have to, but here inflection points, we have to wait. We have to wait. Then you see here, then what we do? We draw a number line, we draw a number line. Okay, we draw a number line, plot the critical points. Okay, plot the critical points.
I have a question.
Please.
So for when you got x equals 0 for the inflection point, you put it, you set the point to 0 and f of 0. So you just plugged in 0 for the original equation.
Yes. Yes.
Okay. And then you got 0 from that.
Yes. Yes.
Okay. All right.
Good.
Thank you.
Okay. Okay. So then number 4, right? So number 5 is increasing and decreasing. And also concavity. How do you find increasing, decreasing first? You use the first derivative, you use the critical points. So draw a number line here, plot the critical points, -20, +20. So don't do this. What's wrong here? We cannot do that, right? You have to put in order. So -20 first in the left hand side, +20 there, because I get that we get that type of answer. So you have to write in order. Okay, so we already have this here, and choose a test point. Choose a test point. And is so how many intervals do we have with these critical points? We have the interval from negative three, right? Negative infinity to 0. I mean negative infinity to -20. -20. Do you include the endpoints? Do you write this way? No, right? So what we are trying to determine, we are trying to determine where the function, where the derivative is positive or negative. Both at -20 and 20, the derivative is 0. Okay, and at these points, critical points, the derivative is 0. They're the turning points. Okay, so what do? You choose a test point here. If you and me both don't see the same thing, then it will be difficult for you to follow. So choose a test point here. Which test point do you choose? -1000? Who can choose -25? Right? Choose a test point here in the interval from -20 to 20. Which test point do you choose? What's the easy one?
0.
Good. And 25 here. Okay, then plug in those numbers, each of those numbers, in the derivative. What is our derivative? X squared minus 400, which can be written in the form, in the factor form of x minus 20 times x plus 20. Now it is easier to plug in this factor form. Now you plug in -25 for x in the derivative. So -25, so we don't care what the value is, we just want to see the sign. Okay, so replace x by -25. -25 minus 20, a negative number. Second factor, replace x by -25. -25 plus 20, and the negative number. Multiply that. What do you get? You get
Positive number.
positive. Good. So f prime is positive here. That means the function is increasing on the interval from -infinity to 0. Okay. So then 20 to -20 to 20. Plug in 0, this 0 for x in the derivative. 0 minus 20, negative. 0 plus 20, positive. Negative plus negative times positive, we get negative. That means the function is decreasing on the interval from -20 to 0. And do the same thing on the interval from 20 to infinity. Okay, 20 to infinity. Okay, so do you see that? So now we have the intervals on which the function is increasing and decreasing. Don't we? The function is increasing on the interval from -infinity to -20 and 20 to infinity. Sometimes, you confuse with these test points and write -20, -infinity to -25. That's wrong. So I suggest you to just cross those numbers out after you are done. Now try to find the intervals on which the function is concave up or down. For that purpose, you see what we got when we set our second derivative equal to 0 and solve for x. We got here here. Okay, we set the second derivative equal to 0 and solve for x. We get x equal to 0. Okay, plot that 0 here in the number line. And how many intervals do we have now? 2, right? Negative infinity 2. 0, comma, 0 to infinity, right? So then determine the sign of the second derivative on each of those intervals, meaning what? You can choose a test point here. You can choose 100,000. You don't have to, right? So, but if you plug in -1 for x in the second derivative here, you get negative on the left side of 0. That means the function is going to go down. On the right hand side, if you plug in any number, it doesn't have to be, you just plug in 1 for x, you get positive. That means function is concave up. Now what do we have so far? We have the domain, we have the symmetry, we have what? We have the critical points, we have the intervals on which the function is concave up or down, when we have inflection points. What do we need? So let's go back and see where we are. So we are here, number 5. On number 5, and find the extreme values. Well, you find out then what? You find out where the local maximum and local minimum are. Local. So we're talking about what? Extreme values, critical points, absolute maximum, right? All these extreme words. So find the local extreme values. So do you know? So look at here. Here in the intervals where the function is increasing or decreasing. So we have two critical points here, -20 and 20. Remember that first derivative test? We did one problem, I think, yesterday. On the left side of -20, the function is increasing. And the right side of -20, the function is decreasing. It should be something like this. So we have local maximum there at -20. Agree with me? So that's also called the first derivative test. You should have that from previous class. Okay. So what is that? If a function, let's say, if the derivative changes from positive to negative at some critical points, the function has local maximum at that point. Similarly, look at 20. On the left side of 20, the function is decreasing. Right side of 20, it's increasing. So it should be something like this. So we have local minimum there. Do you all agree with me? Do you understand that? So local max. Again, -20 itself is not local max or local min value. That's the place where the function has local max value. So you have to find the local max value. Just plug in -20 for x in the origin function and find the value. Okay. And similarly, we have local mean at x equal to 20 and find the local mean is what? F of, you find the number here, you find the number here. Now we have everything we need. And also you can you can easily see that the function has neither horizontal or vertical asymptotes, and you can find out the x and y intercepts, and we graph it. And then when you graph, then make sure that you put that function in your calculator and compare your sketch with the graph that you get in in your calculator. Can you do that? So I will send this slide to you somehow, okay? How do you feel? So I'll stop here.